How you doing, guys? We're looking at geometric series in this section. That's text and test 4, page 344, exercise 4.9. This set of numbers here is called a geometric series because if you go from term to term, you multiply by the same number with each step. Okay, so in this case, you're multiplying by 3 with each step. In part 2, you're dividing by 3 or multiplying by a third with each step. The way you'll establish that a series is geometric in general is to take one term, 27, divided by the previous term, 9, you get 3. That's called the common ratio. And you should find if you divide 9 by 3, any other two adjacent terms, you should also get the same common ratio. So this question says, determine which of the following sequences are geometric. Okay, I'm going to jump down to part 5 here. This one is not geometric. I'll show you why now. You can see 1, 1.5, 1.25. I've rewritten them out as improper fractions here. And you can see really that you're not going to be able to multiply by 1.5 and by 1.5 again and by 1.5 again. But formally, the check might be that 9 over 8 divided by 5 over 4 will not give the same answer as 5 over 4 divided by 3 over 2. Okay, if you do that, what's that going to be? 9 over 8 times 8 over 5. Times 4 over 5 leaves you with 9 over 10, whereas here this is 5 over 4 times 2 over 3, and that leaves you with 5 over 6. So because you don't get the same answer here, it's not geometric. In a geometric series, if you divide any term by its previous term, you should always get the same answer, what's called the common ratio. Looking at question 2, each of the following sequences geometric. Find A, R, and hence find the indicated term. So A, just like before, is the first term. So in this first one, it's 5. R is the common ratio, and you always find that by dividing one term by its previous term. So 10 divided by 5, we get R equals 2. And then hence find the indicated term T11. Now you can just count forward on this, but there's a formula that you can use for this stuff as well. If you go to your log tables on page 22, you can see this formula here is our geometric series formula. Now, why that generates a geometric series? Well, if we have a look at the one that we were working on just now, which was 510 with a common ratio, 510 with a common ratio of 2. So it's going to go 5, 10, 20, 40, 80. Okay. Tn is going to be the first term, 5, multiplied by the common ratio 2 to the power of n minus 1. According to our formula, Tn equals AR to the power of n minus 1. So what's the first term going to be? Well, that's going to be 5 times 2 to the power of 0 when you plug a 1 in there. And that's just 5 times 1, which is 5. T2 is 5 times 2 to the power of 1, which is 5 times 2 is 10. Okay, 5, 10. T3 is 5 times 2 to the power of 2. And that's going to be 5 times 4 is 20. Okay, our third term. T4, you can see is going to be 40 because it's 5 multiplied by 8 or 2 cubed. Okay, so this pattern, excuse me, sorry about that. This pattern, Tn is R to the power of n minus 1, will give us a geometric sequence or generate a geometric sequence. So here we can say, well, Tn is 5 times 2 to the power of n minus 1. And the last term they've asked us about in question 2 was T11. Sorry, so find T11. So T11 is going to be 5 times 2 to the power of 11 minus 1. 5 times 2 to the power of 10. Excuse me. Rambled off the page for a second there. That's 5 times 1024, which is 5120. So that's going to be our 11th term. So the difference between geometric series, I suppose, and the other ones, they grow very, very quickly. Already our 11th term there is very large. Question 4 here we'll have a look at as our last one. Find the value of R given that the third term is 6 and the 8th term is 1458. Now, they should have told us this is a geometric series, but given that it's the section on geometric series, it's probably safe to assume. Okay, so we're going to use our general formula that Tn is AR to the n minus 1. And we're going to say, well, I can say that 6 is AR to the power of 3 minus 1, or AR squared, equals 6. And I can also say that 1, 4, 5, 8 equals AR to the power of 8 minus 1, which is AR to the power of 7 is 1, 4, 5, 8. So these are two simultaneous equations that I have here. Simplest way to solve is to divide this one by this one. So you'll say AR to the 7 is the same as 1, 4, 5, 8. Well, if I divide this side by AR squared, a number that's the same as AR squared is 6. Okay, so I can divide this side by 6. A's cancel, and I'm left with R to the power of 5 equals 1, 4, 5, 8. 1, 4, 5, 8 divided by 6, which is 243. And then R is the fifth root of 243. So how do I find that? Well, I put it to the power of 1/5, 243 to the power of 1/5. That's one way to do it anyway. So I'm going to say this to the power of 1/5, and I get 3 as an answer. So R is 3. Okay, I need to, I'm not finished. That's the common ratio. I need to come back up and say what's A. So this says A, actually let me do this here. A multiplied by R squared equals 6, excuse me, where R is 3. Well, that's A times 3 squared is 6, or 9A is 6. And so A is 6 divided by 9, which is 2/3. Okay, so our pattern is Tn equals A is 2/3, R is 3 to the power of n minus 1. And if we go back and read the question again, the question asked us to find the value of R. Oh, so actually we could have stopped when we had the value of R, but now we know the general pattern as well if we wanted it. Okay, I'm going to ask you now to just go and do questions 1, 2, and 3. So finish 1 and 2 and try 3 by yourself. Tomorrow we're going to do 5 onwards. Okay, so we'll leave it there. I'll talk to you then.